Hello, welcome to the video abstract of our paper Wide-Sense CDF Overbounding for GNSS Integrity, written with my colleagues from Thales Alenia Space France, Odile Mallier, Julie Antique and Sébastien Trille. The need for highly reliable positioning for safety of life applications has led to the development of GNSS augmentation systems like SBAS or ARAIM. These systems rely on the transfer of integrity from the range to the position domain through overbounding, which are mathematical methods to ensure that the position protection level respects integrity with the prior knowledge of the range error distributions. Existing overbounding techniques are based on the CDF overbounding illustrated in the left panel. However, CDF overbounding relies on stringent assumptions on the range error distributions. In particular, it has to be zero mean and symmetric about zero. A second concept of overbounding, called paired overbounding, is illustrated in the middle panel. It does not need these assumptions, but often leads to highly conservative position level protection volumes at the expense of availability. Finally, the more recent two-steps overbounding method illustrated in the right panel combines these two techniques with improved availability, but it is complex to build and evaluate. In this paper, we proposed a new approach called Wide-Sense CDF Overbounding, which offers more flexibility and robustness than existing methods by accommodating biased distributions and relaxing the stringent assumptions of symmetry and unimodality while retaining the original simplicity of the CDF overbounding technique. This method combines CDF and paired overbounding, building on the observation that CDF overbounding, illustrated in the left panel, is equivalent to paired overbounding by a well-chosen pair of distributions, as illustrated in the right panel. The replacement of CDF overbounding by a pair overbounding enables us to relax the assumptions needed for CDF overbounding. The computation of protection level in the position domain is performed exactly the same way as with CDF overbounding, but with an inflation factor, ANK in this formula, which compensates for the weaker assumptions of wide-sense CDF overbounding. This factor depends on the integrity risk and on the number of line of sights, but its value can be tabulated for immediate usage, and the table is given in the paper. The justification with the mathematical proof of integrity is detailed in the paper. Finally, we perform a numerical analysis using real GNSS data that demonstrate the enhanced flexibility of wide-sense CDF overbounding and shows its potential to improve the robustness and performances of GNSS-based safety solutions in various applications. Thank you.